Welcome to Working to Pump Liquids. So the general idea here is we will be looking at pumping a liquid out of a tank. And essentially, instead of focusing on how much is remaining, the pump only pumps so much water at a time, right? So the pump only pumps so much water at a time. The rest of the water simply remains sitting in the tank. No work is being done on that water as it sits. So the rest of the water remains sitting in the tank. With no work being done on it. So instead of thinking of everything moving a little bit at a time, we're instead going to think of a little bit moving the entire distance at a time. So now we will focus on a little bit of water. So a little bit of weight. Moving the entire required distance. So we'll have our sliver of weight essentially multiplied by the entire distance it needs to travel. So I'll do that more clearly in an example. So we'll start off with the example: water is being pumped out of an inverted conical tank, which has a radius 5 meters and a height 10 meters. So we have a inverted conical tank. Which has a radius of 5 meters, a height of 10 meters. We have a pump, which is pumping the water to a spigot 1 meter above the tank. And then our water, essentially what we're going to do is we're going to look at each sliver of water. So we will look at one little sliver of water with thickness dy and calculate the weight of that sliver of water, and then look at how far it has to travel. So what we are interested in, we will focus on a sliver of water, find its weight, and then multiply by the distance that sliver has to travel. I guess I should call it a layer of water, essentially. So we'll focus on a layer of water, find its weight, and then multiply by the vertical distance that layer needs to travel. So if we call the radius of the sliver r, right, the volume of the sliver, or radius of the layer r, the volume of the layer, is, we have the radius squared, pi r squared, times height, which is just pi r squared times dy. Right? So now we need to define our y. Right? So I'm going to take sort of 0 to be on the bottom here. And then I will take y to be how high above the bottom our sliver is, or our layer is y. So we need to figure out r in terms of y. So we need to figure out r in terms of y, where y is the height of the layer above the bottom of the cone, or above the bottom of the tank. So we actually are going to be able to apply similar triangles here. So our large triangle has a short base of 5 and a long base of 10. And then inside that, we have a smaller triangle that has a short base of y and a long base of y and a short base of r. So here we have r is to 5 as y is to 10. This is using similar triangles. Or in other words, y is equal to 2 times r. Or r is equal to 1/2 of y. So what this gives us then is that the volume of our layer is we had pi times r squared, so pi times 1/2 y squared times dy. Or in other words, pi over 4 y squared dy. So this gives the volume of the layer that is y meters above the bottom. So I should specify the height in meters of the layer above the bottom of the tank. So this is our volume. So from here, we need to find the weight. So now we need to find the weight. So we have weight when we're working in the metric system is the mass times 9.8, specifically 9.8 meters per second squared. So we need mass. Now, if we scroll back up to our problem statement, we are told that the mass, or the density essentially, is 1,000 kilograms per meter cubed, or per cubic meter. So we have mass, we have 1,000 kilograms per cubic meter times, we have pi over 4y squared dy cubic meters. And then we multiply it by our 9.8 meters per second squared. So again, I essentially am doing the total volume of our layer multiplied by the density, 1,000 kilograms per cubic meter. So if we simplify this a little, we have that the weight of the layer is given by 1,000 divided by 4 would be 250. If we then multiply by 9.8, we're looking at 2,450 pi y squared dy. So this here, this weight of the layer is the force due to gravity. So this is our force due to gravity for that entire layer. Now that entire layer, so the distance to move this layer we have to go the total of 10, so the whole cone was 10 meters. Our sliver is y meters above ground. So that leaves us with 10 minus y meters to go to get to the top of the tank. And then we have an additional 1 meter to go to the spigot. So the distance to move this layer, we have to go 10 minus y meters to the top of the tank, plus another 1 meter to the spigot. So that makes for a total of 11 minus y meters. So we have the force due to gravity. We multiply by the distance. So the work performed to move that layer so the work performed to move this one layer would be the 2,450 pi y squared times dy. That's the force. times 11 minus y. So this is force and distance it needs to be moved. So this is different from what we've done before. We actually are finding the total work required to move just that one layer of water. And then the integral is going to sum up the work required for each layer. So then the total work for moving all of the water we need to sum up the work required for each layer. So this is the sum of the work required for each layer. And so if we add up all the layers, our layers go from y equals 0 to 10, right? So 0 is the bottom of the tank. 10 would refer to the layer at the top of the tank. Then we put our work for the sliver. So we have 2,450 pi y squared dy times 11 minus y. This is a very odd way of writing an integral. So instead, we will rewrite this as the definite integral from 0 to 10 of 2,450 pi y squared times 11 minus y dy. At this point, we just have another polynomial. So this is 2,450 pi. Then we have times the integral from 0 to 10 of 11y squared minus y cubed dy. Taking that integral, we are looking at 2,450 pi times 11y squared would go to 11 thirds y cubed. Minus y cubed would go to minus 1/4 y to the 4th. We are evaluating from 0 to 10. So this becomes 2,450 pi times 11 thirds times 10 cubed is 1,000 minus 1/4 times 10 to the 4th is 10,000. And then, of course, we have minus 0, plugging in 0. If we go ahead and simply evaluate this, plugging this into my calculator, I'm going to go straight to decimals here. So we have 2,450 times pi times 11 thirds times 1,000 minus 1/4 times 10,000. And I wind up getting 8,979,719.002. So I'm just going to say approximately 8,979,719. And then the units we are working with, we are in the metric system. So this would be working with Newton meters or joules. So this is the amount of work required to pump that entire tank. It was 10 meters tall, radius of 5, inverted cone, to an additional 1 meter above the tank. So again, what we're doing here is we're thinking of it, think of the pump as pumping the top layer at any given point. So that top, whatever layer we have is being pumped to the top of the tank and another 1 meter, but that whole layer has a constant weight. So again, this is another situation where we do use integrals to find work, but the technique we're using is different this time around. Instead of just force times that little sliver of distance, we're looking at the sliver of liquid and finding the force that is always required for moving that sliver of liquid multiplied by the entire distance that it is being moved. We will go ahead and look at one more example of this in the next video.